It seems kind of silly to talk about Cauchy's theorem because there are about 600 Cauchy theorems. Well, maybe not that many, but if you just say Cauchy's theorem to someone with a mathematical background, too many things come to mind. So this is in the context of complex integrals and Cauchy's theorem. And so what we're going to do is look at line integrals. And so what we have is some path in the plane, and I'm going to do that symbolically by giving it a name. A lot of people use gamma, so we'll stick to gamma. And the domain is the closed interval between A and B, and the range is in the complex plane. And what we're mostly interested in are simple closed curves. So simple means that the curve doesn't intersect itself. So if you look at my glasses, this is not a simple curve because you get this self-intersection right here at the bridge of my nose. One lens is a simple closed curve, but so that's a genuine restriction on what it is that we're looking at. And what we're going to do is integrate some function f of z over the curve gamma. So this is pretty typical in more advanced writing of integrals. You just write the domain by some symbol and then f of z dz. Some of you may have studied some things about differential forms, which makes this f of z dz really interesting, but that's not our topic right now, so let's not get distracted. Anyway, there's a simple definition here. There are two definitions. If you read Alfors goes through both and says, yeah, pick the one you like. So anyway, so I'm going to pick one. And this is just straightforward how we do integrals. F of gamma of t, gamma prime t dt. So that's how we, and now this is an ordinary or this is two ordinary integrals like you would have done in Calculus 1. And so not much theory to go behind this. And so that's what we mean when we integrate some function over a curve. And of course, we're mostly interested in f being holomorphic or analytic. And so that's what we're going to be looking at. Let me remind you of something from calculus, most likely calculus 3, I think that varies a little bit, which is Green's theorem, which is also a theorem about line integrals in the plane, and it's widely used in physics and in other areas of mathematics, and there are a lot of generalizations. This whole class of theorems is really called Stokes' theorem, which is not the Stokes' theorem you might have studied in Calculus 3. There's a whole broad kind of integrals. And that says if you're integrating over gamma of some p dx plus q dy, so p and q are functions of two variables, and they've got appropriate smoothness conditions. You can go off down a big rabbit hole trying to worry about how smooth p and q have to be. We're going to try not to go there. Anyway, we're going to do that line integral, and it works out that this is equal to an integral over the area, and I'll just draw some pictures to illustrate this anyway. And I'm going to use this notation, p sub x meaning partial p with respect to x, q sub y meaning partial q with respect to y, and that's an integral over an area. And I'll show you what the area is. The area is what gamma bounds. So if I have gamma appropriately in green, the Jordan curve theorem, which is beyond what we can do in a course whose aim is not to do the Jordan curve theorem. That would be a course in algebraic topology. The Jordan curve theorem says that a simple closed curve, continuous and the like, is subdivides the plane into two regions, an inside and an outside. Of course, that depends on your perspective. And so I'm just gonna say, look, I've got the curve gamma here in green, and the inside, and I hope you noticed, but I'll point it out again. Gamma is going counterclockwise. Counterclockwise is positive. The inside is, I'm going to call this region omega, and the other part of Green's theorem says that the integral is going to be over omega. So there's a picture of omega. There are some very, very complicated pathological examples that you can study in algebraic topology. This isn't algebraic topology, although this is where algebraic topology develops, so maybe it is algebraic topology. But that's the situation. Now, in the case of a holomorphic function, it works out that P and Q have to have certain properties, and so this integral comes out to be much easier than it is. But that's not the best way to think about it. One of the things that we worry about in many areas of mathematics is path independence. And so if I have 2 points, say alpha and beta, and I can imagine having two different paths from alpha to beta through the plane. And the question is, does the integral along this path equal the integral along this path? And there's another way of looking at this, which I'll just kind of do in color. If you take the first path forward and the second path backward, I don't know if this is going to be visible. I'm going to try. Yeah, it's in red. So one path goes forward, the other path goes backwards. That should be a simple closed curve. And so the question about whether a path independence actually becomes a question of whether the integral around that simple closed curve is zero. And that's what Cauchy's theorem tells us about. So there's a theorem in Alfor's that's kind of buried. I'm a little surprised by that, but it's on page 107, right in the middle of the page, and it says that the integral of f dz, we're not specifying the domain, you're going to see why in a second, is path independent. Well, that's why we're not specifying the domain, because we're talking about many different domains. Is path independent if and only if, and this might ring a bell, if and only if f is the derivative of an analytic function. So derivatives of analytic functions, this is just a fundamental theorem of calculus. And so, but now we can come back to where we started. So instead of being the difference of the values at the endpoints, well, the endpoints are the same, so the difference is zero. In many ways, that's just the fundamental theorem of calculus. So that's where Alfor's kind of hides this idea, and so that's fine. So let me look at a very important example, which is just going to blow this all out of the water, and that is the integral over the unit circle of the function 1 over z. So I'm just going to write that as dz over z. That's a pretty common abbreviation that people do with integrals, is they treat the dz as if it's not the parenthesis, it's actually part of it, and they manipulate it. So it's an abusive notation, as the Bourbaki called it. Anyway, this is something that we can do quite explicitly. The unit circle is parametrized by e, I'm sorry, I'm going backwards, all right, e to the I theta, theta going from 0 to 2 pi. So this is the integral from 0 to 2 pi. dz is I e to the I theta. That's on top. The bottom is e to the I theta, d theta. So that's just doing standard line integral stuff and differentiation stuff. The e to the I thetas cancel, and this integral is 2 pi I. So what we're seeing here is a failure of path independence, because if you go along the circle this way, you'll find out that that's not the negative of going along the circle this way, or I'm sorry, not the same thing. If they were the same, this integral would be 0, and it's not. And it's easy to spot where the difficulty is here. The difficulty is that this integrand is not defined or holomorphic or anything nice at all when z is 0. and z is 0 is inside the unit circle. So we've got this business of having what would be called a singularity inside the circle. Excuse my hand there. So, okay, so that's our first problem. So we have a failure of path independence, and this is not 1 over z is not the derivative of any holomorphic function. We've already seen that because, I'm sorry, I said derivative. I meant 1 over z is not the antiderivative. No, derivative, excuse me. There is no antiderivative. It would be log, and log is not a function. It's not multiple valued. And that's because e to the I, e is a periodic function. The exponential function is periodic. So what we're going to settle in on here is this statement of Cauchy's theorem. And it's an interesting situation where we're going to talk about the proof of Cauchy's theorem over a rectangle, which is fine, and then refine that to talk about other areas. And so that's what the big deal about complex integration. So Cauchy's theorem says that if we have a function f that is defined on some domain and holomorphic everywhere in the domain. So the problem with this dz over z integral is that it's not holomorphic everywhere. There's a problem at the origin. That would be everywhere within something enclosing the unit circle. So if we have a holomorphic function, that means that for any path gamma inside omega, the integral over gamma of f is 0. So gamma is some path inside omega. So I guess I can draw a picture. Here's our omega, and inside that we have some path. And so that takes care of the situation that we have. Again, there can be pathological examples, but holomorphic usually gets rid of a lot of pathology, so we don't have to worry about that too much. Okay, that's Cauchy's theorem. The integrals are 0 if we're integrating a holomorphic function. dz over z is not holomorphic in the unit disk. So that's where the difference comes up. And so one of the things, and you might have seen something like this in Calculus 3, is a situation like this where we have two paths gamma, and one's on the inside of the other. The Jordan curve theorem says inside makes sense, and so so I'm going to indicate a region omega by shading. We don't have to shade it too specifically. There is a region omega. It's like an annulus, but it's not really quite an annulus. And if we call the outside path gamma sub O, call me crazy, and the inside path gamma sub I, O for outside, I for inside, then if we have a function that's holomorphic in that kind of annular region, then the integral of over f over gamma O is the integral of f over gamma I. And so that means that if we take, say, the unit circle, there's the origin, and we take some wickety-whack simple closed curve outside of there, we'll call that gamma, the integral over gamma of f is 2 pi I, same as it is in the case of the unit circle. So there's an awful lot of topology that's gone into this, and you can slice up the domain into little nice kind of sort of rectangular pieces, and the line integrals cancel along the common boundaries. Alfors has some pictures about that, and those are pretty common pictures. So what this is going to lead to is the concept of a winding number, and then the Cauchy representation theorem that tells us how to calculate values of complex functions given only what's gone on the boundary there. And there's that. One final word. Alfors really likes Goursat's proof of Cauchy's theorem, and you know what? I like it too. And the thing is, it seems like it's a very complicated theorem, and so let me give you two things about it that should simplify how you see it. One is what we're doing is binary search. We take the rectangle, slice it up into 4 pieces, find where the integral is biggest, do that again, do that again, do that again. And we're working our way down to picking out some point. There's a compactness thing here. Or we could say we're computing a Cauchy sequence in there. And we find some point that's going to be kind of the central thing of what's going on. And then we apply the tangent line approximation. This is the tangent line approximation from Calculus 1. And use that to add some stuff to the integrand that doesn't change the integral, but gets us the tangent line approximation. And using that, Goursat was able to prove that the integral of f over a rectangle was 0 as long as f is holomorphic and actually in a domain including the rectangle. So binary search, computer science stuff, tangent line approximation, elementary calculus. It's a very elementary proof, even though it's complicated. And so, but there it is, Cauchy's theorem. All your integrals are 0 except when something bad happens. God,